welcome to this problem walkthrough. In today's session, we'll be exploring LeetCode problem number 929, titled Unique Email Addresses. We'll break down the problem, analyze different approaches, and guide you to an optimal solution. Let's get started. The problem asks us to determine the number of unique email addresses from a given list, based on specific normalization rules. Each email consists of two parts: the local name, which is the portion before the @ symbol, and the domain name, which is everything after the @. In the local name, any periods, represented by the dot character, are ignored, meaning alice.z and alices are treated as the same. Additionally, if the local name contains a plus sign plus, everything after the plus is disregarded during normalization. For example, Alice plus 123 and Alice are considered identical. The domain name, however, remains unchanged. By applying these rules, we can normalize each email and count how many distinct normalized emails exist in the list. The output of the problem is a single integer, representing the count of unique email addresses after normalization. Let's look at an example to understand the process. Suppose the input list of emails is test.email plus alex@leetcode.com, test.e.mail plus bob.cathy@leetcode.com, and testemail plus david@lee.code.com. When we normalize these emails, the first one becomes testemail@leetcode.com because both the period and everything after the plus are ignored. Similarly, the second email also normalizes to testemail@leetcode.com. The third email becomes testemail@lee.code.com since the domain name remains unchanged, and the plus is handled in the same way. After normalization, the unique emails are testemail@leetcode.com and testemail@lee.code.com, which gives us a final count of 2. In another example, let's consider the input emails @leetcode.com, b@leetcode.com, and c@leetcode.com. Here, none of the local names contain a dot or plus, so no changes are made during normalization. The unique emails remain as @leetcode.com, b@leetcode.com, and c@leetcode.com. Since all three addresses are distinct, the output is 3. Now taking a different scenario, if the input is test.email plus alex@leetcode.com and test.email.leet plus alex@code.com, the first email normalizes to testemail@leetcode.com, while the second becomes testemail@code.com. These two are distinct, so the output in this case is 2. To break it down further, in the last example, the first email test.email plus alex@leetcode.com is transformed into testemail@leetcode.com because the dot is removed, and everything after the plus is ignored. The second email test.email.leet plus alex@code.com becomes testemail@code.com after removing the dot and trimming the plus portion. The resulting unique emails are testemail@leetcode.com and testemail@code.com, leading to an output of 2. The problem also defines constraints, such as the input list containing between 1 and 100 emails, and each email having a length between 1 and 100 characters. Edge cases to consider include lists with only one email, addresses that lack plus or dot, and scenarios where the domain names differ while the local names are identical. These details ensure that we handle all possible inputs correctly and robustly. To tackle the problem of finding unique email addresses, we can start with a brute force approach, which follows the problem's constraints directly. The main idea is to normalize each email by processing its local name and domain name separately. First, we split the email into the part before and after the character. Then, in the local name, we remove everything after the first plus character, as it is considered irrelevant. We also eliminate all dot characters since they have no impact on the uniqueness of the email. Once the local name is cleaned up, we combine it with the original domain name to reconstruct the normalized email. These normalized emails are stored in a set, which inherently ensures that only unique entries are kept. Finally, the size of the set gives us the number of unique email addresses. This approach is straightforward and adheres well to the problem's instructions, but it does involve repeated string operations for each email, which can become inefficient as the input grows larger. With a time complexity of O, n asterisk m, where n is the number of emails and m is the average length of each email, and a space complexity of O, n asterisk m, for the set, this method is simple but not the most optimized for large datasets. Next, we can refine our approach by identifying ways to optimize the normalization process. One key observation is that we can process the local name in a single pass, avoiding redundant steps. Instead of splitting the email into parts and performing multiple operations, we can directly process the local name up to the @ character. While doing so, we can skip any characters after a plus and ignore dot characters altogether, as they do not affect the result. Once the streamlined processing is complete, we concatenate the cleaned local name with the domain name to create the normalized email. This optimized approach achieves the same functionality as the brute force method but reduces unnecessary intermediate steps, making it more efficient. The overall time complexity remains O(n*(m), but with fewer redundant operations, the actual runtime is improved. Space complexity also stays at O(n*(m) for storing unique emails in a set. While this approach is slightly more complex to implement, it provides a cleaner and faster solution to the problem, making it a strong candidate. An alternative approach to consider is using a hash map instead of a set to store the normalized emails. In this method, the hash map would keep track of the count of each normalized email. While this doesn't change the overall time and space complexity, it could be useful if we needed additional information, such as the frequency of each email address. However, since the problem only asks for the count of unique emails, a set is both sufficient and simpler. Ultimately, we chose the optimized approach because it offers a streamlined normalization process while maintaining clarity and efficiency. The brute force method, though straightforward, involves redundant operations that can be avoided. On the other hand, the hash map approach introduces unnecessary complexity for this particular problem. By focusing on the optimized approach, we strike the best balance between performance and simplicity, ensuring that we address the problem requirements effectively without adding unneeded overhead. In this problem, we want to determine the number of unique email addresses in a given list, but the challenge lies in the fact that some addresses may appear different at first glance but are actually considered the same after applying specific normalization rules. These rules focus on how the local name, which is the part before the @ symbol, is processed. First, anything after the first plus symbol in the local name is ignored, as it's considered irrelevant. Second, all dot characters within the local name are removed, as they don't affect the actual address. Importantly, the domain name, which is the part after the @ symbol, remains unchanged throughout this process. By applying these rules, we can compare emails based on their normalized forms and count how many unique addresses truly exist. To solve this problem, we start by defining our input and output. The input is a list of email addresses, and the output is the number of unique normalized email addresses. The first step is to initialize a set to store these normalized emails. A set is particularly useful here because it automatically handles duplicates, saving us the effort of manually checking for them. Next, we iterate through each email in the input list. For each email, we split it into two parts, the local name and the domain name, using the @ symbol as the delimiter. For example, in the address user.name plus alias @gmail.com, the local name is user.name plus alias, and the domain name is gmail.com. Once we've separated these components, we can begin normalizing the local name. The normalization process for the local name involves two key operations. First, we remove everything after and including the first plus symbol. This can be done by splitting the local name at the plus symbol and taking only the first part. For instance, user.name plus alias becomes user.name. Second, we remove all dot characters from the local name. This is achieved by replacing each dot with an empty string. Following this step, user.name becomes username. After normalizing the local name, we reconstruct the full email address by combining the normalized local name with the unchanged domain name, separated by an @. For example, username combined with gmail.com results in username@gmail.com. This reconstructed email is then added to the set. If the email is already in the set, it won't be added again, ensuring no duplicates are stored. Finally, once all emails have been processed, the size of the set is returned as the count of unique email addresses. To understand why this approach is efficient, let's consider some key insights. Using a set simplifies the logic significantly because it automatically filters out duplicate entries. This not only makes the implementation more straightforward but also improves performance. Regarding time complexity, normalizing each email involves operations like splitting and replacing, which are O(k), where k is the length of the email. Processing all n emails, therefore, takes O(n*(k). Adding an email to the set is O1 on average, so the overall complexity remains O and *k. For space complexity, the set requires O, U *k, space, where U is the number of unique emails and K is their average length. This is because we store only the unique normalized emails. As for data structures, the set plays a crucial role in ensuring uniqueness with efficient insertion and lookup times, while strings are used for intermediate steps like splitting, replacing, and reconstructing the email addresses. It's also important to handle edge cases carefully to ensure the solution works reliably. For example, if the input list is empty, the output should simply be 0. Emails that don't contain plus or dot in their local names should be processed correctly without any unnecessary modifications, such as user@gmail.com, which remains unchanged. We assume that all input emails contain exactly one @ symbol, as any deviation from this would indicate invalid input. Additionally, duplicate emails should be identified correctly regardless of their order in the input list. To illustrate, consider the input list, test.email plus alex@leetcode.com, test.email.leet plus alex@code.com. For the first email, the local name test.email plus alex is split, and after removing plus and, it becomes test email. Reconstructing with the domain results in testemail@leetcode.com. Similarly, for the second email, the normalized form becomes testemail@code.com. Adding these to the set results in 2 unique emails, so the output is 2. The solution to the unique email addresses problem is implemented in the number unique emails method within the solution class. This function determines the number of unique email addresses after applying normalization rules. The algorithm begins by initializing an empty set, unique_emails, to store normalized email addresses. A set is used because it automatically handles duplicate entries, ensuring each normalized email is only added once. Next, the function iterates through the list of email addresses. For each email, it splits the string into 2 parts, the local name and the domain name, using the split at method. The domain name remains unchanged, but the local name requires normalization. The function processes the local name by splitting it at the first occurrence of the plus character and taking only the part before the plus. This removes any portion of the local name intended as user-specific comments. Additionally, all dot characters are removed from the local name using the replace dot method. Once the local name is normalized, it is concatenated with the domain name using the symbol to form the normalized email address. This normalized email is then added to the unique_emails set. After processing all the email addresses, the function returns the size of the unique_emails set, which represents the count of unique normalized email addresses. The algorithm is efficient, as it processes each email in linear time and leverages the set data structure for fast membership checks and insertions. The overall time complexity is O, n *m, where n is the number of emails and m is the average length of an email address. The space complexity is O, n *m, due to the storage of normalized emails in the set. This implementation handles all edge cases, such as empty input, duplicate emails, and varying local name formatting, ensuring robustness and correctness. This is the Java implementation for LeetCode problem number 929, unique email addresses. The logic directly mirrors the Python solution provided, with changes specific to Java. Key differences include the use of Java's string methods, split and replace for string manipulation, and a hash set for storing unique email addresses. The method iterates through the input array, normalizes each email, and adds it to the set. Finally, the size of the set is returned as the count of unique email addresses. Here, we're working through the problem of normalizing email addresses to find unique ones. Let's start with the input list of emails. The goal is to process each email, normalize it, and add it to a set of unique emails. First, we initialize an empty set called unique_emails. Now, let's process the first email, test.email plus alex@leetcode.com. We split it into 2 parts, the local part, test.email plus alex, and the domain, leetcode.com. Next, we remove everything after the plus in the local part, leaving test.email. Then, we remove all periods from the local part, resulting in test email. Finally, we combine the cleaned local part with the domain to form the normalized email, testemail@leetcode.com, and add it to the set. The set now contains one email, testemail@leetcode.com. Moving to the second email, test.e.mail plus bob.cathy@leetcode.com, we follow the same steps. After removing everything after the plus and the periods, we get the same normalized email, testemail@leetcode.com. Since this email is already in the set remains unchanged. Now, let's process the third email, testemail plus david@lee.code.com. Splitting this email gives us the local part, testemail plus David, and the domain, lee.code.com. Removing everything after the plus results in test email. Since there are no periods in this local part, it stays as test email. Combining the local and domain parts gives us the normalized email, testemail@lee.code.com. This email is new, so we add it to the set, which now contains two unique emails, testemail@leetcode.com and testemail@lee.code.com. Finally, the size of the set, or the number of unique emails, is 2. In this example, all the emails are variations of the same address. The input list includes a.b plus c@domain.com, a plus c@domain.com, and a.b plus xyz@domain.com. We start by initializing an empty set for unique emails. Processing the first email, a.b plus c@domain.com, we split it into the local part, a.b plus c, and the domain, domain.com. After removing everything after the plus, the local part becomes a.b. Next, we remove the period, leaving ab. Combining this cleaned local part with the domain gives the normalized email, ab@domain.com, which is added to the set. The set now contains one email, ab@domain.com. The second email, ab plus c@domain.com, is processed similarly. Splitting gives the local part, ab plus c, and the domain, domain.com. Removing everything after the plus leaves ab, and since there are no periods, it remains unchanged. Combining with the domain results in the same normalized email, ab@domain.com, which is already in the set, so the set remains unchanged. Finally, we process the third email, a.b plus xyz@domain.com. Splitting this email results in the local part, a.b plus xyz, and the domain, domain.com. Removing everything after the plus gives a.b, and removing the period leaves ab. Combining this cleaned local part with the domain results in the normalized email, ab@domain.com. Since this email is already in the set, there are no changes to the set. At the end of this example, the set contains only one unique email, and the final output is 1. In this example, the emails differ only by their domains. The input includes user +1@domain1.com and user@domain2.com. First, we initialize an empty set for unique emails. Processing the first email, user +1@domain1.com, we split it into the local part, user +1, and the domain, domain1.com. Removing everything after the plus leaves user, and since there are no periods, the local part remains unchanged. Combining this cleaned local part with the domain gives the normalized email, user@domain1.com, which is added to the set. The set now contains one email, user@domain1.com. Next, we process the second email, user@domain2.com. Splitting gives the local part, user, and the domain, domain2.com. Since there is no plus or any periods, the local part remains user. Combining it with the domain gives the normalized email, user@domain2.com, which is new and added to the set. The set now contains two unique emails, and the final output is 2. The time complexity of our solution can be understood by analyzing the operations performed on each email in the input list. First, splitting the email into its local and domain parts involves scanning the string, which takes O(m) time for an email of length m. Over n emails, this step contributes O(n*(m) to the time complexity. Next, processing the local part requires two operations, splitting at the plus character and removing dot characters. Both of these involve scanning the string and take O(m) time per email, or O(n*(m) collectively. Finally, concatenating the process local part with the domain part to form the normalized email is a simple string operation, which also takes O(m) per email, adding another O(n*(m) overall. These steps together result in a time complexity of O(n*(m) for the solution so far. Adding the normalized email to the unique _emails set is another critical step. On average, inserting into a set is an O(1) operation per email, but in the worst case, where hash collisions occur, it can degrade to OK, where K is the number of unique emails. Since K is at most n, this operation is O(n) in the worst case across all emails. Combining this with the previous steps, the total time complexity remains dominated by O(n*)m. Now, considering the best and average cases, these occur when set operations remain efficient, keeping the complexity as O(n*)m. In the worst case, even if hash collisions degrade set insertion to OK, the solution is still dominated by the email processing, so the overall complexity remains O(n*)m. The space complexity of the solution is also O(n*)m, and we can break this down further. First, the unique_email set is the primary space consumer, storing up to n unique normalized emails, each of length O(m). This results in O(n*)m space usage for the set. Temporary variables created during processing, like the local and domain strings, each have a length of O(m). Since at most two such strings exist at any time, they contribute O(m) to the space complexity. Finally, the input list itself occupies O(n*)m space, as it contains n emails, each of length O(m). Combining these, the total space complexity is dominated by the unique_email set, leading to O(n*)m. When comparing this solution to a naive approach, the benefits become clear. A naive solution might manually compare each email against all others to check for duplicates, resulting in an O(n)² time complexity due to the pairwise comparisons. This approach uses O(1) additional space, but the trade-off is an inefficient runtime for large inputs. In contrast, the current solution reduces the time complexity to O(n*)m by leveraging string normalization in set operations, significantly improving execution time for large datasets. While the space complexity increases to O(n*)m because of the set, this is a worthwhile trade-off for the performance gain. The linear dependency on n comes from processing each email individually, while the linear dependency on m arises from string operations like splitting and replacing. Together, these factors yield a total complexity of O(n*)m for both time and space, making this solution far more scalable than the naive approach. One of the most common pitfalls when solving this problem is ignoring edge cases. For example, if you don't account for inputs like empty email addresses, emails missing the symbol, or invalid formats, your solution might fail under certain conditions. It's crucial to validate your input thoroughly before moving forward with processing. Another frequent mistake is improperly handling duplicates. If you're using a hash table or set to store unique emails, you must normalize the emails first. Without normalization, duplicates might not be recognized correctly. Overcomplicating the logic is another issue to avoid. Adding unnecessary steps, like repeatedly splitting the email address or using redundant nested loops, makes your code harder to read and less efficient. Simplicity and clarity should always be priorities. Misunderstanding the problem's rules is another challenge. For instance, you need to ignore dots in the local part of the email and stop processing at the plus symbol. Failing to implement these rules accurately can lead to incorrect results. Lastly, remember to optimize for both time and space. Using multiple intermediate data structures or not leveraging in-place operations can make your solution inefficient, especially when dealing with large datasets. Aim for an approach that balances simplicity with O(n) efficiency in both time and space. Now, let's consider some insights that can help you during an interview. This problem is a classic example of string manipulation combined with the use of hash tables or sets to ensure uniqueness. Recognizing patterns like these is key when tackling similar challenges. One optimization opportunity is to normalize emails directly during processing instead of creating multiple intermediate lists. This minimizes unnecessary memory usage and keeps your solution efficient. Communication is equally important. Before jumping into the implementation, explain the normalization rules to your interviewer, like ignoring dots or handling the plus symbol. This not only shows your understanding but also ensures you're aligned on the problem requirements. Testing is another critical step. Make a habit of discussing edge cases, such as invalid inputs or scenarios with large datasets. Explain how your solution handles these situations to demonstrate thoroughness. Additionally, solving related problems can help you build a strong foundation. For instance, the longest substring problem also uses hash tables for unique results, while group anagrams and palindrome permutation focus on pre-processing and manipulating strings efficiently. These offer a broader context for refining your problem-solving skills. Finally, let's look at some alternative approaches to solving the problem. A brute force method would involve normalizing each email and checking for uniqueness using nested loops. While this is straightforward to implement, it's inefficient for large datasets due to its n² time complexity. The trade-off here is simplicity in exchange for scalability. A more efficient approach is to use a hash set for uniqueness. With this method, you normalize each email on the fly and store it in the set. This ensures an optimal n time and space complexity. It's fast and practical, though it requires extra space for the hash set. If you're seeking to reduce space usage further, an in-place normalization approach can be considered. Here, you modify the input array directly by normalizing emails as you iterate and checking for uniqueness in a single pass. This reduces memory overhead but might not be permissible if input modification is restricted. Each approach has trade-offs, so understanding the constraints and requirements of the problem will help you decide which strategy is most appropriate. Great job making it to the end. Today, we covered the unique email addresses problem, focusing on string manipulation and algorithm optimization. Keep practicing and refining your skills. Every step brings you closer to coding mastery. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!